So yeah, typical talk, Mnesia plus LevelDB, sort of match made in heaven, if you like. And it started like we want to get rid of the limitations of DETS, which are horrible, but it also brings us some other improvements. So hence the and more. Myself, I've been involved with Erlang since the mid-90s. I took a detour for about 7 years where I worked on performance analysis tools in the HPC, that's high-performance computing market. So lots of C and assembly programming, some C++. But since late 2013, I'm back in the fold, working for Klarna on the transaction engine written in Erlang, and basically taking care of the database. Right. So why do we want to do this? So here is a summary of the benefits we get from this combination. We get faster node restart times, which is a huge deal for us, because that's a limiting factor for us. We get less RAM pressure. I don't know if you know about Klarna systems, but they are reputed to be among the largest in terms of RAM capacity that run Erlang. And that's also a problem for us. So reducing the RAM pressure would either let us put more stuff in there or possibly buy smaller and actually faster machines. Mnesia currently has a number of a priori limits on table sizes. And depending on how you represent your table, you also get limits on the actual DB sizes. By putting the tables in LevelDB, you avoid those limitations. Now, this talk mentions LevelDB quite a lot, but the work that's been done to Mnesia is completely generic. So if you're sort of interested enough in a different local storage engine that is not LevelDB, it could be anything, then all you need to do is to write the appropriate plugin module as a driver, register that with Mnesia, and voila, you're up and running. And in conclusion, LevelDB works quite well for us. We still have some ways to go in rolling it out, but we are using it live. We have been using LevelDB live for a year now. And we haven't seen a single data corruption or a single core dump from the LevelDB driver. So it actually works well. This is a picture. I apologize for the poor visual formatting, but whatever. So to the left here, you can see, what Mnesia is today. So you have the database interface, that's the Mnesia application. You have a couple of available local storage types. Typically, you would choose between disk copies and disk-only copies. There are 2 more, but they don't really count. Those then map to, like for instance, disk-only copies maps to DETS, which then goes to file. And if you choose disk copies, it maps to ETS, that's in RAM, and disk log, that's on disk. And believe it or not, this figure is actually what Google Slides suggested denotes direct access or core memory. And the real old-timers would recognize why this might be related to core. It's a drum, right? What we've done is we have Mnesia Ext, which extends Mnesia, so you can have a different backend than the ones that are predefined. To this, we have the actual backend, which is Klarna LevelDB. We ignore that for a while, and in the bottom we have eLevelDB, which then talks to disk. This guy here, the LevelDB manager, is something we've introduced in order to be able to handle backups online without taking tables down or disturbing the application while we do backups. And over here you can see who's written what. I will repeat this as we go along. Oh, yes. So the application, in our case, will sometimes, depending on the data set, either go to Mnesia and then down to for instance, LevelDB, but we can also go straight to LevelDB through this LevelDB manager. So some of our data areas do not use Mnesia, but they go straight to LevelDB. So this is a brief, what will happen now? This is a brief overview of what's going to happen. Summarize Mnesia and its problems, summarize LevelDB, talk a little bit about the glue, talk about some of the migration jobs we've done and what we learned and what we did. And then I'm going to finish up with how we solved the backup problem and some pending improvements. Okay, so Mnesia is the standard database application you get with OTP. It's not the its type of database is that the table is a collection of tuples, but all those tuples have to have the same shape. So basically, you declare a record in Erlang, and that gives you the arity of the tuple and the tag of the tuple. You select one of the positions in the record to be your primary key, and those pieces of information you put in the schema, and then you can get a table in Mnesia with that. So you can't have tables with differently shaped tuples, for instance, or tables with keys in different positions depending on the tag in the tuple. So you would have to have different tables for that. Most tables are sets, but you can also have order sets or bags. And accessing a table, you would, depending on your programming style and your requirements, you can either do just key-based lookups and insertions. Or, well, the insertions you give them an entire tuple, but you can do key-based lookups. You can do pattern-based lookups, and you can have these high-level queries, the so-called QLCs. What Mnesia really gives you is persistence, replication if you choose to use it, transactions with the usual guarantees you get from that, and internally locking to make sure everything goes right. So that basically turns it into a proper database. And it also handles things like schema changes online. That's all I'm going to say about that. Now, Mnesia, the thing we care about at Klarna is the available backends. So that's the storage options you have. One of the two main ones are disk-only copies. And when you say that the table is of this type, it's stored in what's known as a DETS. You all know what an ETS is. That's an in-RAM table. A DETS is sort of mirroring that, but it's stored on disk in a file. And it's actually a big hash table, but in a file. The thing to know about DETS is that the data itself is always on disk. There's no internal caching of the data. Whatever internal caching it uses is only for metadata. Like, for instance, if you repeatedly add and delete records, you're going to get unused space in the DETS file that you need to manage and reuse. And that metadata to do that is in RAM. But the actual payload is not in RAM, ever. DETS has a number of problems. Since the data is on disk, you have to do I/O all the time. Obviously, the operating system page cache can help you a bit, but it's never going to be as fast as having it in RAM immediately. The real killer is that the table size is limited to 2 gigabytes. This has been a problem. People have known about it for at least 15 years, maybe longer. 2 gigabytes was certainly probably considered large in the 90s, but it hasn't been large since the advent of commodity 64-bit machines. And that's like 2002, 3 or so. Which means that if you have a large table, of this type, then it can't actually be a single physical table. It has to be split. We call that fragmenting. And this also means that you need some administration to monitor table sizes. So you're introducing a risk here. If your tables grow and you don't have a strategy for fragmenting them, then you may end up with a system that blows up in your face if you don't do something. Also, if you have an unclean shutdown, for instance, if the system crashes, which for a system that's supposed to be up 24/7, that's the normal reason why it would ever restart. It had a crash. So you get an unclean shutdown. Then all these DETS tables are going to be marked dirty. Well, most of them will be. And so when you restart, Mnesia will go through them and say, oh, this is dirty, I have to repair it. And you can't do anything about that. Well, a little bit, but not much. But the end result is that your restart is going to take a lot longer because of this. Shutdowns are also slow. I've been trying to figure out exactly why. I don't quite know why, but they are slow as well. The other main storage option you have in Mnesia is disk copies. Those are completely different. So first of all, they keep a complete copy of the current table contents in RAM, in an ETS table. And all reads and writes, etc., to this table are directed directly to the ETS table. So that's basically as fast as it gets in Erlang. So that's good. Now, for persistence, disk copies use two so-called disk log files. Those are sequential log files that contain terms formatted in a slightly funny way. One of those, the DCD file, contains a complete image of the table from a previous point in time. That previous point in time could be 5 seconds ago or 5 weeks ago. It depends. The other disk log file, the DCL file, contains the pending updates. That is, the updates that Mnesia has accepted and performed for you. So they are in the table, logically speaking, but they haven't made it into the image file yet. But they are on disk, so they are persistent. Occasionally, when Mnesia thinks that the log file with pending updates has grown too large, it will dump the in-core or in-RAM image to disk and produce a new DCD file. Those dumps, I will talk about them in a minute. One nice thing about disk copies is that unlike the disk-only copies tables, there is no a priori size limit on them. So essentially, they could be arbitrarily large. But they have their problems as well. They do slow down restarts, but for a different reason. And that's because, by definition, the entire table contents has to be in RAM. Which means that if you have, like, let's say you have 1 terabyte of data in disk copies tables, and your node restarts, then you have to read that 1 terabyte of data into RAM before your application is up. That takes time, a lot of time. The other thing is that if you have a large table and it is performance critical, that is, you want it accesses to it to be as fast as possible, then you declare it as disk copies. But since it's large, then it will also consume lots of RAM. RAM is not used as a cache of the hot data. It actually copies all of it, whether it's hot or not. So it's actually poor RAM usage here. And these table dumps to produce fresh snapshot files, they cause spikes in system load, which disturb the system as a whole. There are, I mentioned this more as in parentheses, there are other local storage options. One is called RAM copies. These are not persistent. They can be stored in file, you can ask Mnesia to dump the table to file, but there is no automatic synchronization between what you have in memory, in the DETS file, and what's on disk. You have to ask Mnesia to make that synchronization, which means that they're not really database tables in any real sense. We don't use them. I don't know if anyone uses them. The other is that there is a remote type, which is not a local storage option really, but it really says to Mnesia, hey, you don't have a copy, it's over there. So ask that guy for it. We don't use those either. Now, so in summary, Mnesia suffers from high RAM consumption. Because if you want speed, then you have to use these copies tables, but since you have a lot of data, you have to suck all that in, hence high RAM consumption. Both this fact and repair of DETS tables, if you have unclean shutdown, means that restart times are long. And the disk-only copies tables have this 2 GB size limitation. Now, LevelDB is something completely different. It's a key value store. There are many of those around. So what it provides semantically is no different from anyone else, really. What's unique about LevelDB, or rather not unique, but since there are many of those nowadays, but its thing is that it uses these log-structured merge trees. It's a special way of organizing data on disk. Traditionally, like a couple of decades ago, everything was stored in B trees. These structures are very different. Data is automatically compressed, which is good, and it's stored in chunks in files, and these files are then grouped according to age. So there is a sequence of levels from 0 to n. Typically n is 6, so you have 7 levels. And the oldest data would then be in level 6, and the youngest data in level 0. It's based on a library from Google, which is open source. This library is actually the open source re-implementation of Google's Bigtable. But they couldn't open source it back then because it had big and complex and had lots of dependencies on Google internal stuff. So they rewrote it, simplified it, and that's LevelDB. Now, our friends at Basho, I don't know if anyone is in the room right now. I've talked to them before. So they use LevelDB as a backend for React. And in doing so, they've done a lot of work on improving LevelDB, fixing robustness issues, fixing performance issues. Importantly for us, they provide eLevelDB, which is the NIF, which allows us to import LevelDB into Erlang. Without that, we couldn't access it directly. We would have to use some form of network connection to a C node or C++ node. That would kill performance. All of this is open source. And the APIs are what you would expect. Get and put and delete by key. And an iterator API, which allows you to iterate through the table or iterate from a given starting point to the given key. This is what the top level of an actual live LevelDB instance might look like. So at the top we have the log file. This is a memory mapped file. I will talk about it in a minute. There is the manifest file. This one lists all the SST files, the small data chunk files that you have, and contains metadata about them. And we'll see how that's used. And then we have a number of directories with SST files according to the different levels. And you can also see that the SST files are of varying sizes. That's in part because of compression, and part because of how they're produced. You may actually, when you produce them, you may actually throw away obsolete data, but you've already committed to producing the SST file, so you may not produce as a large SST file as you might otherwise do. Now, writing in LevelDB, you have this fixed size write buffer. The size is configurable, but when you create your instance, that determines the size. So that's a log file. This is mapped into the LevelDB library, and all the writes are simply memory stores. They do not do explicit I/O. But because the file is mapped, things actually work out okay anyway. So writes are actually blazingly fast. When this buffer is full, so semantically we have a key value store, so a set of keys and corresponding values. So the contents that are in the file in the buffer when it's full is sorted and put in what's known as a sorted string table, an SST. And then created as a file in level 0. So if we go back here, so one of these files in level 0 is what you would get when the write buffer fills up and you export it. The manifest file lists all the SST files and metadata, including the key ranges that are contained in that specific SST file. And that is used for searches. Now, as we produce data, so we write to write buffer, it fills up, we produce a new SST file, it goes to disk, we continue writing. Obviously, after a while, we're going to have a lot of these SST files. And there's going to be redundancy there. For instance, we may have deleted keys. We may have rewritten keys that we rewrote a long time ago. So we have to do something to not just fill the disk, and that's the compaction phase. Basically, what it does is that it focuses on a particular level, and then it takes the SST files at that level and merges them into the next level. The next level, those are the older files. As a result of compaction, LevelDB produces new SST files and deletes old ones. It does not edit the SST files once created. And that's critical. And we'll see why. This compaction thing runs asynchronously in the background, so you don't have to worry about it. It's also one of the things that Basher has worked on to make smoother and more effective. So the original LevelDB could sometimes sort of stall due to this, but Basher has done some work to alleviate that. So this is what could happen. To the left, we have two levels. We have SST1 and 2, which are sort of semi-old, contain the keys or records for keys A and C and D and E. And from our write buffer, we recently got SST3 with bindings for keys B and E and the deletion of key D. And let's say now that the compaction kicks in. Oh, and we also have the manifest file, which describes all these files appropriately. So as a result of this, we're going to produce new files, SST4 and 5. So when we merge SST3 and 1, we get a file containing bindings for keys A and B. They're sorted. And when we merge SST3 and 2, we get SST5 with bindings for keys C and E. So E is now rewritten, and the old entry for key D is gone. And also the manifest is updated. Now, reads, they basically go in age order. So they start looking in the write buffer. If it's not there, LevelDB then looks in the manifest to identify the candidate SSTs using the key ranges. And then it basically searches those from the youngest to the oldest until it gets a hit. The Bloom filters, I'm not sure if that's a Basher invention or Basher just improved them. But the Bloom filter, the SSD files can also contain Bloom filters, which are an additional way of sort of getting quick rejection of searches. There is no explicit caching here. So to get read performance, LevelDB relies on two things: having an ample supply of file descriptors, which allows it to keep many SSD files open. And if an SSD file is open and is memory mapped, then it only has to go to memory to do a search. If it has to access a file which is not open, then it has to close some other file, open the one it needed, map it, and then do the search. So that's a bit slower. So it uses file descriptors and M-mapping for caching. And then the actual data caching itself, it relies on the operating system, so-called page cache. And this is a deliberate design choice by the LevelDB implementers. Okay, now, Mnesia Ext. How do we tie these together? So Mnesia Ext is a big patch to Mnesia. I know 9,500 lines sounds scary, but most of it is boilerplate, so it's not that scary, and it's actually heavily tested by now, so it works. What it does is that it adds an interface to Mnesia schema, which lets you declare a new table type or a storage type. So in addition to disk copies and disk-only copies, and the other two we don't use, you can declare a new type, for instance, LevelDB copies. And then you say that tables of that type are handled by Backend, which is named by this module here. And you are in total control of both the name of the type and, of course, the module. Once you have that, you can then create tables as usual. And you just, in the table definition, just use this type name, the storage type name you invented. The way Mnesia discovers that this table is of this newfangled type is that the table info call for storage type returns a tuple ext, and then the name of the type, and then the name of the module that handles that type. Now, you as a application programmer usually don't need to worry about this. Mnesia internally, and this is the reason why the patch is so big, Mnesia internally calls table info storage type all the time to figure out, okay, what is this table represented like, and given the particular operation that we want to do at this particular point, we then dispatch on the table type and do different things. And this is all inline code in Mnesia. It's not pretty. So what the patch does is basically every time Mnesia does one of those dispatches, there is there is a new clause which matches on ext, the ext tuple, and then it simply redirects to this backend module and calls a specific function there. And of course, the function is called depends on the context in which this operation occurs. So basically, this is what Mnesia should have been implemented like from the start, rather than having these hard-coded cases. Mnesia Ext has been in development by Ulf Wieger for I don't know how many years, but many years, long before we started thinking about using it at Klarna. But a couple of years ago, Klarna decided that let's try to make this reality. So we contracted Ulf to finish it up and also to interface it with LevelDB. And this, I guess, finished more or less a year and a half ago. Some fix-ups like a year ago. But yeah, so it's basically finished now. Rika Karlsson sits over there, has been working with Ulf on tidying up the patch and integrating it into the version of OTP we use at Klarna. I've been working on testing the damn thing, fixing corner cases that Ulf missed, all the things you need to do to get it into production and actually converting tables and so on. And the entire process of converting tables and so on, all the tickets and review requests you have to submit. This is not quite open source. You can find it on GitHub if you know where to look, but I don't think it's on a sort of under a Klarna label yet. No, I think it looks a bit stale, but yeah. So there are copies in the wild, but not quite the latest one. But it will be open source, trust me. Now, Mnesia X itself doesn't know about LevelDB. It's totally generic. So you need to have a backend module, and that's Klarna LevelDB in this case. So it bridges the gap between Mnesia X and eLevelDB. Again, it was originally written by Ulf. I now maintain it. It's about 3,000 lines of Erlang. Not too scary. A big gen server, basically. And the reason it's big is because you have these two worlds. In Mnesia, you have a table is a set of tuples, and the set might be an order set or a bag. In LevelDB, you have a key value store. One key, one value, period. So you need to bridge that gap somehow, and that's basically what this module does. So it maps between two sets of and so on to the key value module. It maps tuples with keys to key value pairs. In this case, what it does is take the tuple, it erases the key, replaces it with the empty list, because that's a nice small term. And then it has the original key and the value which lacks the key. That's the stores, and then when you retrieve it, it puts the key back in and hands it over to Mnesia. That's just to avoid storing the key twice. Bags are handled by basically inventing a new key space where keys are also numbered. It's a bit ugly, but so are bags. Also, it implements higher level operations like select using the iterator API. And for reasons I don't really understand, it also handles secondary indexes. I think this is a design flaw, but we haven't done anything about it. Basically, there is no reason why secondary index should have to have the same type as the base table. It's just a table. So it should have the same flexibility as the main table. But right now, index tables have to be in LevelDB if the main table is in LevelDB. Also, it maintains metadata for some operations, like, for instance, the table info size call. This is problematic. I will talk about it near the end. So let's see what time it is. Oops. Okay, we have done some migrations. The first one did not use Mnesia at all. It was a big bunch of text files stored straight down in a file system. One XML blob per file. And it used a hashing algorithm to spread these across 1,000 directories. One of the problems with this data store was that the number of files and the large sizes of the directories meant that backups we basically couldn't do them. And things like an operator was not allowed to go into the machine and type ls in one of these directories because that would stall the machine. So that's a risk. At this time, this data is from a year ago. At this time, these files contain 160 gigs of actual data. If you just open them and see how many bytes are there in the file. But in the file system, they consumed almost 300 gigs. That's because of fragmentation. Once we put it in LevelDB, it consumes 68 gigs. And that's largely due to the automatic compression. So there's a nice gain there from almost 300 gigs to not quite 70 gigs. I did some performance measurements on accesses, and we could easily write in the order of, say, 40 to 100 gigabytes per second. Reads were in a small, sort of more narrow band, but totally acceptable performance numbers. So one thing you will notice is that LevelDB is faster at writes than reads. And the spec of the machine is 2-generation-old HP 580 with 40 cores. I did try Berkeley DB. Now, I don't know if how many of you have tried to use Berkeley DB with Erlang, but that's problematic because there's no good open source binding for it. There's supposedly a good one that is locked up in Synapse, but that doesn't help us. So I wrote a simple one, so probably really bad. What we saw there was that Berkeley DB does read faster than LevelDB. Not a whole lot faster, but faster. But writes to Berkeley DB was totally terrible, like 2 orders of magnitude slower. So this just confirmed to us that no, we are not going to use this. The migration itself, since the files were stored in the file system, there was both an internal API and a lot of code that just forgot about the API and went straight to the file system. That had to be cleaned up because everything has to go through the API once we put it in the real backend. Testing we did side by side for verification and also to be bug compatible. For instance, LevelDB will return OK when you delete the record, whether or not that record exists or not. Whereas when you do it in a file system, you will get different return values depending on whether the file actually existed or not. We didn't really want to play games with the application, so we made the LevelDB backend mirror what the file system did. There were also some other things that the file system did, like for instance, it maintained modification times of files. It turned out that the code used this. So we had to adjust the backend to emulate this behavior and actually keep file modification stamps with the records. Migration was very careful. We did it first on a single node, did it non-destructively, so we ran it side by side. We monitored the hell out of it to make sure that nothing broke. And we also kept an option, since we did this non-destructively, to disable LevelDB if it had acted it up. Fortunately, it never gave us any problems, so we completed the migration and did it on all the other nodes as well. Pack files are similar. They are Erlang terms, not XML blobs. Lots of files, lots of directories, difficult to do backups. They had a huge size shrink when we put it in LevelDB, from 600 gigs to 40. The process we went through with side by side and all of that was basically the same as with the Pcache. The main difference is that the backend was simpler because we didn't have to emulate so much of the file system semantics. Once we took this live, we have a job which is really heavy on reads to these pack files. Now we were afraid that this might go slower, but it turned out that the job itself got something like a 2x speed up. That was a big deal. We have converted the disk-only copies tables. I'm not going to talk about that. And we have not converted the disk copies tables yet. We are in the process of doing that right now. I did a trial conversion of a smallish table yesterday. So it was 15 gigs in the disk log files. When I converted to LevelDB, it's like 5 gigs, so only a third. The beam process shrunk in size by roughly the size of the disk log files. And the startup time just with this table, an empty database, but this table, only non-empty, was 4 minutes 40 seconds faster. Now, this is one table, not a very big one. So imagine we have hundreds of tables. So, yeah. We think that moving to LevelDB will do wonders for restart times. Now, the problem we have is backups. The reason is that our backup strategy wants to do backups sort of semi-online. What we do is that we basically block writes during the backup phase so that Mnesia will not do any writes. And then we can sort of ask tar, basically, to archive all the files. While this is going on, reads are permitted, obviously. However, LevelDB emphatically cannot be backed up while open. Don't even try that. The reason is that this backend compaction thing can run at any time. So even if you're not actively writing to the database, there can be internal writes and rearrangements going on, and you have no control of that. The only way to avoid those is to close the database, or close your handle to the database. But that, of course, prevents reads, which isn't quite compatible with our model. So the trick is to do what are called quick snapshots. Since the SSD files are immutable, what we can do is that we can close the database, we create a shadow directory, we do a hard link of all the SSD files, and even if there are hundreds, maybe 1,000 files, this is quick. You copy the log file, the manifest file, then you're done, you reopen the database, you're back in business, and then you can offline do an archive of your snapshot. Quickly, the LevelDB manager implements the necessary logic to allow this to happen without disturbing Mnesia or the rest of the application. It basically implements a shared exclusive lock, exactly like a multiple readers single writer lock. The API is compatible with LevelDB, so it's a drop-in replacement or a drop-in wrapper. It's quite small, like 400 lines of Erlang, plus a small supervisor. This is how you do a backup. And for a 100 gig table, it's offline less than a second, so you can do backups this way. I have 2 slides left. Some improvements. So maintaining metadata for this table info call, that is hugely problematic because the nice thing about LevelDB is that it's fast at writes. Slightly slower than reads, but fast at writes. What happens now is that every time you do a write or a delete, the backend from Mnesia to LevelDB has to do a read in order to check if the record existed or not, in order to know how it's going to adjust the cached size. So unfortunately, right now, writes imply reads. So we're not getting the performance benefit from fast writes. We are working on, we've eliminated all the frivolous use of table info size from the code. We've implemented sort of alarms in the backend if it gets asked for this for a large table. And basically that's silent now, so we know that we've gotten rid of it. And the next step is to change the backend so that it doesn't do this anymore. The other problem is this LevelDB manager, whose only reason to exist is to be able to do online backups. If it wasn't for that, we wouldn't have it in the stack. So it causes latency to operations. So we think that this functionality ought to be in eLevelDB itself. That would solve those problems nicely. Yeah. That's it for me.
Okay, thank you. I think we can afford some quick questions.
Thank you. Did you try to develop DETS to overcome its limitation, and if so, how is that?
Rickard?
I've been working a few years ago now. We did some work on a 64-bit version of DETS. We had a master student doing most of the groundwork. We got it mostly working, but it's basically not a very good idea. The properties of DETS, how it's structured on disk, the way it sets dirty flags and tells you that you need to do a repair on this because you did an unclean shutdown. That sort of works if the data, if it's just 2 gigs in the file. If you have a 100 gig file, that doesn't scale. So it's probably not really a good idea anyway. So we basically abandoned it. Nobody really wanted it.
Anything else?
Yeah? They work. Yep. QLCs don't work right now. But they might work if we do a bit of...
What is special in QLC that makes...
They require a bit of additional interfacing to the backend. That's not in place.
You can get, with respect to the transactions in Mnesia. Mnesia offers a transactional API.
Yeah?
So what happened there when you use it?
So in this case, when we combine Mnesia with LevelDB, you will get actually atomicity redundantly, because Mnesia itself will serialize with respect to this table, and then the LevelDB itself is, all the operations there are atomic. So, yeah.
Any reason why Mnesia Ext should not be in the Mnesia code?
Not really. Just it's been under active development, and we are sort of swamped with work.
Yeah, I can give a short answer. So as he said, Ulf has been working on this on and off during many years, and it's only recently that it's been that this big, pretty huge patch has been cleaned up enough that OTP might consider actually including it. So we hope we'll be able to push it to OTP relatively soon, now that we've verified in production that this stuff works.
Nothing else? Well, thank you, Michael.